All right, let's get started. I think we have most of the students. Today, we are going to talk about timing analysis. This is actually a pretty important lecture. This is going to be very important for you guys to understand how this asynchronous system works. And also some of the concepts that I'm going to talk about, for example, setup time, hold time, and clock skews, some of them may not be that intuitive, at least at the beginning, to some of you. So please make sure that in case you cannot follow, right, just ask me the question. Okay, just chime in. Either type in the chat window or just stop me. All right. Okay, so a few announcements. You guys probably have seen your prelim 1 grades, right? If you look at the overall performance, I think it's pretty encouraging. So the high score is 54, right? Just one point shy of the full mark. Median and average, it's around 41.1, between 0.1 and 0.3. So if you translate the score, it's about 75, right, out of 100 points. This is actually definitely not a trivial exam. So I'm actually pretty happy with the performance of the class. Also, I understand that there's a lot of challenges. There are a lot of challenges with the remote learning, online learning, and also this Zoom-based online exam also caused some trouble, right, to some of you. Again, I'm pretty happy, right, with the average. Overall, the class did very well. I also understand that for some of you, the score that you saw might be slightly lower or lower than what you expected. So this is totally fine, right? So don't be too concerned. We still have 2 more exams. We have prelim 2 and final, so both of them carry more weights, right, than prelim 1. But if you're indeed concerned, right, about your performance for prelim 1, feel free to shoot me an email. Okay. We can arrange a one-on-one meeting. I can offer you some tips, so which usually help us based on my past experience. Okay, and also we're gonna curve this thing right at the end, so we will grade on the curve. Already mentioned on Piazza. I'm gonna talk about, so what does the median mean? Right now I don't have a good idea, right? So it doesn't mean B, B plus, or maybe even A minus, right? We'll talk about it after prelim 2. So I'll have a pretty good idea after the second prelim. Okay. All right. So also, if you have regrade requests, right? So just go to the website, right? So we have a form for you to fill out and just send it to us within a week. All right. Okay. So also want to remind you guys, lab 2, this is the last part, right? Let's do on Wednesday. Make sure that you guys either go to TA office hour or go to lab hours to check it off. This is required. And going forward, we're going to be releasing lab 3 pretty soon. Right, going forward, you guys will be doing this in 2 student group. We actually have an even number of students in this class, turns out. So I think most of you already have already formed the group, right? For lab 3, you can either stick to the same group, okay, or you can choose, if you are interested to get to know more people, right? You actually want to find a new partner, that's also fine. Okay, you can use this a find teammate feature, right, on Piazza, or let us know if you need help with the team. Okay. All right, so just a quick recap, right, of some of the things that we covered last time. I'll ask you guys about this D flip-flop, right? I keep asking you guys about D flip-flop because this is basically one of the essential building blocks, right, for sequential logic and also for synchronous system. Right, so we talk about the Moore machine, right? No surprises, right? 2 states, right? S1, S0, S1, and also ask the class, right, to do a Mealy diagram, right, from the DFF, right? Some of you seem to think that we can actually get away with just single state, which turns out to be, right, this is actually incorrect, right? If you actually direct logic, we're going to see, for this one, we're going to see something like, basically the output Q will be, right, directly, right, connected to D, which is not sequential, right? This is wrong. The actual Mealy diagram, right, the correct one looks like this, Okay, so make sure that you guys convince yourself this is indeed correct. You can do that this transition output table. Right? The key thing is for, we actually talk about, maybe let me come back here first, right? So the reason this is incorrect, right? The Q cannot be directly connected to D, because think about the definition of D flip-flop, right? When we first introduced it, so the Q next, right? Equals D. This is the right equation, right? If you translate it into the terms, the new terms that we are familiar with now, right? Hopefully, so with FSM, so really we have something like this, right? So Q, right, should be right equivalent with the current state, right? And next state is D, right? So this is the basically how we represent DFF, right? Using either Moore or Mealy diagrams. Okay. And the reason we care so much about this flip-flops, right? Because we are actually interested in using this so-called synchronous system. With a synchronous system, so this is where all these flip-flops, they are synchronized by a global clock. Okay. And if you look at this system, right, so we basically update the states of these flip-flops every clock tick, right, at every triggering clock edge. In our case, in our convention, usually we just use the rising edge. And these are all synchronized, right? So we update the flip-flop at the same time, simultaneously, at each clock tick. The opposite to a synchronous system, there's actually something called asynchronous circuit or asynchronous system. Actually, there's a book chapter, I think there's a section, maybe a small section, short section in the book. You can take a look. So with an asynchronous system, this is opposite, right? So there we do everything. We do the communication using handshakes. And we can have the sender and recipient, right? So sender will send a request and the recipient will send acknowledgement. So we do this so-called local handshake to complete the data transfer. So this is the other opposite, right? The other extreme. Actually, the mainstream. So if you look at most of the digital circuits this day in the market, right? So that we use. So they're mostly synchronous system because they are indeed more easier to design and verify. We do use asynchronous system in some cases, but they are still a niche right now. Okay. Maybe I can give you an analogy, right? If it's still not too clear to you, right, what exactly is a synchronous system? So, for example, if you think about our exam, right, Turing 1, it is a synchronous system, right? Make sense? Okay, it is indeed clock, right? So everyone's supposed to arrive, right, at 1 p.m. Okay, and we are gonna collect your result 75 minutes later, right? I'm not gonna ask you, I'm not gonna bother you, right, in the middle exam, and I'm not gonna ask you, I'm not gonna do this handshake, right? I'm not gonna ask you, are you done? Are you done? Are you done? Right? So, all you need to make sure that you basically make your exam ready before this clock edge, right, which is 75 minutes later. So this is very much a synchronous system. We are going to use this analogy maybe a little more later on when we introduce other terms. Okay, hopefully this makes sense. And the important thing is, so we do have this, right? Usually we do need to compute, right? We do have this combinational logic sandwich between these flip-flops. So when we do the compute using the combinational logic, so we want to make sure that the result, right, output of this combinational logic, they need to settle, they need to be stable before the next clock edge, right? The triggering clock edge. So this is really important. Okay, so what do I mean by settled, right? What do I mean by stable? So let's try to be even more precise here. So again, let's look at the clock edge, right? So this is the rising edge. Now, we are looking at the, let's say, D flip-flop, right? So the input side is D, right? Over here, I'm using this sort of a hexagon kind of a shape, right? Like this, right? So basically this hexagon indicates, a stable signal. It can be either 0 or 1, right? It's not exactly the same as the waveform that we are used to, right? But we are just using this hexagon to indicate the stable signal. And this crosses, right? So this means that we are transitioning from one value to the next value. Okay. So for us, right, to be able to, for the flip-flop be able to capture this D input, we actually need to make sure that, so the signal of D is stable within this sort of decision window, okay, right around the clock edge. So the important thing that I want to mention here is that actually there are two parts of this decision window. So one part is called setup time, the other one is called hold time. We actually need to make sure that the signal is stable, okay, for a period of time, because setup, right before the clock edge, and it needs to be held stable also after the clock edge for another period of time, which is defined by this so-called T hold. Okay. And why exactly do we have to have this requirement? This is actually beyond the scope of this lecture and also this class. But later on, if you're interested, I can post some additional reading material. This is very much related to how we actually implement this flip-flop using CMOS logic. Okay. But we do need to make sure that the signal is stable, right, before and slightly after. The textbook actually has a very good analogy. So we are basically capturing the signal, right? The textbook I think has an analogy like when you are taking a picture, right, using your camera, you actually right at the time, right, when you push a button to take the picture, you actually want to sort of hold your hands steady, right? So that's the analogy. Okay, again, so D value must be stable, okay, during this decision window. Okay, for some period of time before, that's called setup time, and after, which is the whole time. Okay. All right. So if you look at this waveform, right? Again, this is actually another waveform, right? Another term that I want to introduce is this TFFPD. Okay. So see here, this is a Q value, right? The Q output from the D flip-flop. Any guess, right? By just looking at the name, what does this mean? What is TFFPD? Flip-flop period, flip-flop delay. Right, so very close, the delay time of the flip-flop. Okay, so right, Alma, right. So that's a more precise definition, propagation delay of flip-flop. Okay, so basically, there's also logic. Think about flip-flop, right? So we do have logic inside the flip-flop. We already mentioned that we are no longer living in this ideal world, right? So where all the gates have zero delay. We also have gates, right? We also have logic inside the flip-flop. That means, right, after clock edge, right, after the flip-flop captures the new D value, it also takes some time for this new value to propagate and to show up, right, on the Q side, the Q output side. So this is basically the TFFPD. Right? So last time we talked about this PD, right? PD is the shorthand for propagation delay, and FF means flip-flop. And in some cases, people also call it clock to Q delay. So this is where when do we expect to see the change of Q, right, after the clock edge. This is the clock edge to the change of Q. So that's why it's called clock to Q delay. And we're going to be using this delay as well in this lecture and later on. So just want to make sure that you guys are aware of this, this delay, right? It's not like the flip-flop is an ideal device. It also has delays. Okay, any questions? All right. Okay, if not, so let's look at the scenario where this D input is actually not stable right around the clock edge. So what's going to happen? Okay, so here's the template that we're going to use a lot in this lecture. Okay, we have a pair of flip-flops, right, and some control delay. So over here, if you look at this waveform, we're focusing on this flip-flop, this the second one. Okay, and we have the clock waveform here. So if this D, right, so here it's making a transition, okay, right at the clock edge. So this is actually bad. So this is where the flip-flop may capture neither 0 or 1. This is where we have so-called metastable state. Okay. Again, this transition for D2, okay, over here. So I'm saying it's happening inside the decision window. If that's happening, we have something called metastability, or we have a metastable state. Remember this the element, the storage element that we have, the latch, flip-flop, they are supposed to be bistable, We have something called bistable element, They are supposed to be in either 0 or this 1 state. But if indeed, so this D, the E input is not stable, like this, during the transition window, then there's a high likelihood that this Q, the state of the flip-flop, will be sort of undetermined. It's neither 0 or 1, and it will remain undetermined for a period of time. Okay, that is actually unbounded, unfortunately. But the longer you wait, the more likely that you will end up with a stable state later on. But hopefully this is clear to you. This is not a good idea, So to make a transition at this window. Okay, so again, this is called metastability or metastable state. When the D input is not stable, we may end up in this state. Okay. All right. So I think there's some question. What does the hexagon mean? Okay. So we are having this. The reason we are using the hexagon is because these one are stable values, but this can be either 0, 1. Okay, based some value. If we already know the value, then we just draw the waveform like this, But I just want to use this hexagon to indicate this is some value. Okay. All right. Is it clear? Come on.
I guess what I was confused about was I thought that D is unstable, like when it's crossed over.
Oh, okay. Good question. So by unstable, I mean that it's making a transition, in this period. So yes. So basically as we need to make sure that D is stable, So what we want to make sure that D is either 0 or 1, So during this window. But what we have here is you look at these two hexagons, So we are actually changing from one value to another value during this window. Okay. So that's why I have like two hexagons over here. If it's stable, then we just have one hexagon. If there's no transition. So what I meant here is that there should not be any transition during this window. Okay. Right. This is just a sort of abstract way to indicate that there's some value. Okay. Amanda is asking, will it actually have a value of neither 0 or 1, or will it? Good question, Amanda. So in this metastability, in this metastable state, that could be literally just between 0 and 1, like 0.5, 0.6. Or after a certain period of time, it may stabilize into 0 or 1. But we don't know. Okay, so this is actually probabilistic. All right. Okay, so this is that, So basic Q is undefined if this happens. But eventually, so like I said, it's going to move to something stable, but it may take a while. Okay. Also, last time we talked about glitches, This is another review. I just want to make sure that everyone still get intuition. We talk about the 2 input mux, This is 2-to-1 mux. This one may have some glitch, If you look at the waveform, so initially over here, X and Y, they are both assigned, so they are actually steady, They are ones, X and Y. Since they are steady, there's supposed to be no glitches, Since this is a mux, So it doesn't really matter what is S, Whether 0 or 1. F, the output is supposed to be 1, Output is supposed to be 1. But somehow, if you look at this diagram, so S is making a transition, over here. S is making a transition from 1 to 0. Okay, but for some reason, there's this glitch, There's this hazard, we call it static hazard, F is making a dip temporarily, we call it transient value from 1 to 0 and then back to 1. Okay. Really the reason is, okay, see here, so you want to look at this part, okay? So this is where, okay, we are seeing the transient, right? So for certain period of time, so both of these terms, right, they are 0. Okay, that's why we are seeing this dip, right, where f is going down to 0 for a moment. So why is this the case, right? So why do we have this this gap, right? So somehow s and y and this right, this term s and y and s naught and x, they're not making the transition at the same time. That's actually causing the dip, right? So what is the fundamental reason, right? It's already in the slide, but I want to ask this question anyway. Just want to make sure that you guys are. Right? Last time I gave you some, right? So I showed the transition, right? So per signal, and explain how that might happen. But more fundamentally, it's really about. So we have these two passes, right? You look at this circuit diagram, right? We are traveling. The signal need to travel a longer path, right? On the top. So that's where S naught and X, right, may respond to the change of S slightly later than this path, right? So we basically have a slower path here, a longer path here, and we have a faster path at the bottom. Okay, and when these two, right? So since this path is lagging behind for a moment, so this is what causing this gap, right? And which eventually leads to this dip, this glitch, right? So in other words, so it's already summarized here. Okay, so these glitches are typically caused by the unequal signal propagation delays in the circuit. Make sense? Any question about this one? I was asking, could it be solved by another clock between S? So you want to make the clock faster or slower? So first, let's assume that, okay, going forward, let's assume that we have a global clock. Right? I'm going to talk about clock skews, right? So we do have different endpoints for a clock, right? But let's first assume that we do have a global system clock, okay? Since we are dealing with a synchronous system, right? In practice, for more complex circuits and chips, in many cases, we do have different clocks for different subsystems, and that's where some asynchronous circuit will be useful, some sequential logic will be useful. But in our class, we just assume that everything that is synchronous globally. Right, you have a global clock. But at least in this case, right, this dip, right, this glitch is not causing any harm, right? It's harmless because the F becomes stable, right, right before the clock edge. So that's where we capture the right value. Make sense? But what about this case? Is it still correct or this is wrong? This is wrong, right? It's bad. So what's the difference if you compare this two? Let's just, I want to make it really obvious here by flipping between these two slides. Right. So the glitch is happening at the clock edge, right? But can you guys give me a more intuitive reason, right? Why this glitch is happening at the clock edge? You will between just compare this to diagram. Yes, right. Ambrose, you're right. So see here. So in this case, we have a wider cycle time, right? We have a wider clock width, right? In this case, this is where it's good. And in the second case, right, this is a bad situation. Right? We sort of narrowed the clock width. So we are running at a higher clock frequency, right, in this case. So if you're not careful, indeed, some glitches may cause us issues, right? Hopefully this is right, this is intuitive enough. Right? But the question, of course, right, the obvious question is, how fast should we run the clock? We need to determine that, right? We need to analyze the system, and we need to determine what is a safe clock period. Otherwise, we may end up with scenarios like this. So this basically, again, this is wrong, right? This leads to the main topic of this lecture. Right? So we actually need to analyze the system. We need to figure out what exactly, right, is the clock. So how fast can we run the circuit? We really want to avoid this failure, right? So we don't want the parts to be too narrow, right? So we want to avoid the metastability. We don't want this input to make a transition at the clock edge. We also don't want this logic to glitch, right, at the clock edge. So that's where we need to make sure that the clock parse is not too narrow. So these things should not happen. Right? Input cannot change too soon, right, before the clock. So this is where we have a setup time violation. Cannot happen. I cannot change too soon after the clock edge. Right? This is where we have a hold time violation, and we really want to meet this specification. So this is our task. Okay, this is the task of the designer, the architect of this chip or this circuit. So how exactly do we determine this? So this is where we need to learn this so-called sequential circuit time analysis. Okay, and this is the keyword, right? So we want to do time analysis. Actually, Quartus, right, the head tool you are using has algorithm that does this kind of a time analysis automatically for a circuit to determine the safe clock period for your design. But let's try to understand this, right? So let's try to manually analyze our circuit first. Of course, we are only going to focus on the simple ones. So first, we want to make sure that, so given the circuit, so we need to calculate this delay between all pairs of flip-flops, okay, within the circuit. Since this is a synchronous design, right? They're all synchronized by a single clock. We may have more than one pairs of flip-flops that are communicating. We actually need to look at all pairs. And okay, we need to make sure that we meet the setup time requirement. Okay, so basically the input to the flip-flop has to be stable before the clock edge. So that's where we need to make sure the clock cannot be too fast, right? The parse of the clock cannot be too narrow. And we have something called hold time as well. Right? And this is where we have to look at the, hopefully this will be more clear later on. We need to look at the minimum propagation delay when we analyze the hold time. And we look at the maximum propagation delay when we look at the setup time. Interestingly, for hold time, I'm going to briefly explain. It's actually, when we analyze the hold time, it's independent of the clock frequency. When we analyze the setup time, we very much need to determine the clock frequency. Okay, it's actually not the, although it's kind of counterintuitive, right? But since hold time happens after the clock edge, right? So hopefully it's somewhat clear to you. So that's where the cycle time does not matter much. Okay, so these are still the sort of the abstract things, right? I'll make it much more concrete, but these are the three things, right? So we need to look at all the pairs, although in many cases we will just look at a single pair, and we need to care for the setup time and the hold time. Okay. All right, so more terms, and also maybe like a bit more. Okay, I need to give you guys a bit more acronyms. Okay, but the good thing is that we have already seen most of this. Okay, again, this is our template, right? So we have a pair of flip-flops, FF1, okay, FF2. So we assume the normal convention, right? So we have this. This is the D side, right? This D1, this is Q1, D2, Q2. Right? So the left-hand side is input, right-hand side for flip-flop is the output. And we propagate right through this combinational logic. Right. So given this template, let's take a look at some of these definitions. Right. First, we have of course, right. This is a clock period, right? T clock, and we have already looked at this. Right. So this is the FFPD, right? Flip-flop propagation delay. So over here, this crosses means that the value is not stable yet. the cross is inside the hexagon means that the signal is not stable yet. Okay. It's going through some transition. And we have this, okay, TCOM. So this is the delay of the combinational logic. Okay. And of course, we have another clock edge right over here. So this is the clock edge. Right before the clock edge, we have setup time. This D2 needs to be stable before the setup time, then needs to remain stable, okay, for a period of time during this whole time. Okay, so these are the key definitions. Any questions about this diagram and these terms? And we're going to be using this a lot in this lecture. Right. Yeah, so right, where exactly does this setup time and hold time requirement come from? Right, like I mentioned, this is sort of beyond the scope of this class. Right, this is actually very much related to how we implement the flip-flop using CMOS logic. I can send you guys some additional link, right, if you're interested. But for now, this is something that we have to memorize. Okay, so we basically have to hold the D value steady during this window. Okay, it's going to take me some time, right, to actually explain why do we have T setup and T hold. So we'll just abstract it away, right? Okay, so let's look at setup time constraint. So we need to make sure that we meet the setup time, right, so that we can capture the right value. So how exactly do we analyze this? So how do we connect these different things, right? So we have T clock, right? We want to determine how wide this clock period should be, right? How wide the cycle should be. And we have these parameters, right? FFPD, these are constants. FFPD, complete delay, and setup time, and T hold. These are given. These are not variables. These are given. And we want to determine T clock. We want to know like how what is the T clock? What is the best clock frequency for us to be running this circuit safely? So how exactly do we tackle this problem? Let's first look at setup time. So one trick, which I find very useful, and I highly recommend that you guys later on use it as well when you analyze this kind of diagram, especially for dealing with this time analysis, is to use some reference time. Okay, for example, if you look at this clock edge, let's name this this time as T0. Then we can just say this is a time 0. This is the reference. This is my reference time. And we're going to be using this a lot, okay, later on. I can ask you over here, what is this? What is this? What is this time? This is basically 0, right? Of course, T0 plus T clock, right? Since we already defined T0 to be 0, so this is basically T clock. Right? Nothing interesting so far, right? Are you guys still with me? Right? Nothing interesting so far. But we want to make sure that this setup time, right, requirement is met, right, is honored. So that means the input. So this is our deadline, right? So this is like a deadline over here. So we have a deadline here. Basically D2, right? The input, either the input to the first flip-flop or the input to the second flip-flop. But let's just focus on the second flip-flop for now. Okay. Doesn't really matter actually, right? Since all the flip-flop capture the input, right, at the same time. This is a synchronous system. But let's just focus on, let's say we focus on flip-flop 2, right? So D2 needs to be stable, right, before this deadline. But when exactly is this deadline? Let's just extend this line. What is this time? Can you guys tell me? What is this time? This is what? Based on our reference time. Okay. Very good, right? T clock minus T setup, right? Okay, so far so good. Okay, so this is our deadline, right? Now let's look at how exactly do we calculate the arrival time of this D input. These are our parameters. Right? It takes some time to propagate through the flip-flop, and it takes some time to propagate through the conditional logic, right? Okay, so when is the D input available? Okay, let me just rewrite this, right? So, this is the T clock, right? This is the T clock, and this is our deadline, right? Which is T clock minus T setup, right? So when is D available? Okay, very good, right? So it's available over here. Okay, this one at this point, this is basically TFFPD, right? And TCOM, right? So this is a TFFPD plus TCOM. Is it clear? What's the relationship between these two? This is the arrival, right? The arrival of D. What's the relationship between arrival and the deadline? Strictly less than? Very close. Actually, in our case, this is fine. Okay, less equal is fine. Okay. As long as we are right before the deadline, this is fine. Okay. Any questions about this relationship? If you understand this one, you pretty much understand how we calculate the setup time, how we calculate the setup time requirement, and how we determine the clock period. So basically, add up the propagation delays, right? Of course, we want to take the worst case, right, the maximum propagation delay, and then we look at the deadline. The deadline in this case is defined by this term, okay, and we use less than equal. That's it. All right. Yeah. So deadline also greater than, right, greater or equal. That's also the same. D is available means that it can be read, right? Yes, by saying D has arrived or D is available, I mean that D is steady, D is stable. Okay. We need to make sure that D is stable, right, before the deadline. It's still not clear, right? Analogy, right? It's a flip-flop propagation delay. Coming back to the exam analogy, it's sort of like the time that you need, right? When we give you the link of item pool, right? The time you need to open up the link, right? To basically open the exam. And then the TCOM is basically the time that you need to actually, right, do the questions, right, solve the questions, solve the problems. And setup time, it's basically like the time you have to make sure that you preserve some time, right, for scanning the exam, right? And after you scan and upload to CMS, you don't want to throw away your exam right away, right? Just in case the TA find that, the project find that the exam you uploaded to CMS is corrupted. Okay, you also actually want to keep it for a while. This is actually not a precise analogy, but I hope that this is somewhat helpful. Okay. All right, so there are more questions. What about, man is asking, what about the unstable bit between deadline and arrival? Oh, so you're asking about this one, right? This one, right? So this crosses basically means that we are propagating the signal. So basically the D2, right? So this signal is not stable yet. That's why I'm using this crosses. Is it clear? Right. So basically they're not stable yet. It takes time for the output to be stable. Okay, so if this is clear, then we can actually rewrite. We already got what we have, right? So we just have to rewrite this this way. Okay. Now what we have is basically T, right? TFF PD, not P. FFPD, right? Plus TCOM. equal t clock minus t setup, right? This is what we got. And if we just rearrange the term a bit, this is the equation. So that's how we determine the cycle time. We basically add up these three things, and we can determine the maximum clock frequency or the minimal cycle time. Of course, we want to make use of the worst case, right? The worst case is where we consider the max propagation delay and the longest path. Okay, so that's the worst case scenario. And this is usually where we consider worst case temperature, right? Also the worst case manufacturing conditions and such. Any question about this?
I have a quick question.
Go ahead.
Can you go back to the previous slide?
Yes.
So on the flip-flop inputs, what about the, I think Amanda was asking this as well, like the unstable parts between like arrival line and the deadline line, like do we just disregard that?
This part?
Okay. No,
this one?
The part before T setup, the one after that. So in between.
Oh, so Curtis, this part?
Yeah, so do we disregard, like, can we like consider that as 0 then inside the equation?
Oh, this is what Amanda is asking. Free-flop input. Yes, so yeah, I see. Yeah, I see this diagram is sort of confusing, right? Don't worry too much about this, right? But in this specific case, basically, all we want to say in this diagram is that the free-flop input needs to be stable right before the setup time, right? Although in certain specific case, right, we may have the Y period, right? So before this, right? So this may not be crosses, right? So basically, this may be stable, right? Over here at this point. Okay, this the free-flop input can become stable over here. That's also possible.
Okay, so like it can have like,
yes.
So like the delay can be there, but it also could be 0, so there is no delay.
Yes, that's right.
Okay, thank you.
Right. As long as the flip-flop input, right, the D input is stable. So this is what this diagram is saying. Okay. Although this gap can be narrow or can be wider, right, depending on the actual combinational delay. All right, good question. Okay, so let's quickly do an exercise. Right. So also I'll give you guys a quiz right after this. So make sure that you guys ask questions. Here's the setup. Right? We have two flip-flops and some parameters. I give you the minimum combinational delay and also maximum combinational delays for both flip-flop and the conditional logic, also setup time and hold time. So just tell me like what is the best achievable cycle time. You guys do some quick calculation. This is a table, right? So first we need to pick out the right numbers. We do need this one. We do need setup time, right? And we also, since we are considering the worst case for setup time, we actually need to focus on the max, right? So we need to pick out this number and this number. Very good, 12. Okay. And we don't need, since we are focused on setup time, we don't need this one. We don't need hold time. Also, we don't need to consider the minimum one. Right. The reason this is 12 is we basically add up three terms, right? F of PD, which is 2, the max combinational delay, which is 7, and then setup. Okay. This is 12. This is the minimum cycle time or the maximum clock frequency. Right. The maximum clock frequency is basically 1/12 nanosecond. Right. This is our frequency. Okay. Right, almost asking about the hold. Let's worry about the hold later. Okay, so for now, let's first, we usually focus on, we handle one at a time. We first handle the setup time, and let's worry about the hold time later. Actually, these two are sort of independent. Okay. All right, 12. Any more questions before you guys